Alright, here we are again. It is the last day of June, June 30th, 2016, and here we are for the penultimate lecture of ENGR 2301 Engineering Statics. So, let's get started. A few example problems again, to finish up the material on centroids. And now, let's see. Determine by direct integration the centroid of the area shown. Express your answer in terms of A and H. So we have this region here, and we wish to find the centroid of it. Well, let's see. We have y equals h times 1 minus k x to the third, like so. Or we can say, any questions? Oh, okay, sorry. H minus k x, or actually, yeah, k h x to the third, like so. Now, the let's see here. The integral for we need to find the x and y centroid. So let's first get, say, the x component. And again, we remember that x bar, the x coordinate of the centroid, is going to be qy over a. Yes? Do we need to find k in terms of a and h? Let's see. We may need to. Actually, yeah, I think you're probably right there. Let's find k in terms of a and h first. Yes, that probably would be better. Before we even do anything else, that'd probably be better. Now, we know that y equals, let's see, h times 1 minus k x to the third. And then, let's see, we need a point. And I know one point on this graph will be a comma 0. So everything needs to be in terms of a and h. So a, or 0, equals 1 minus k, or let me just put the h in there so people don't ask me where it went, a to the third. A to the third. And then this leads to 1 minus k a to the third equals 0. K a to the third equals 1. And so therefore k equals a to the negative 3. K must equal a to the negative third power. All right, then we can, this then makes our equation y equals h minus, let's see, a to the negative third. Or let me just put it as, I'm just trying to distribute this h. Let's see, h over a to the third x to the third. And that's this term here. That's the original equation. Okay, then I know that the first thing I'm going to need is my area. And so my area is going to be equal to the integral from 0 to a of this equation here, of h minus h over a to the third x to the third dx. And let me just go ahead and pull the h out. Maybe I shouldn't have distributed that. That's okay. H integral 0 to a of 1 minus x to the third over a to the third dx, which equals, let's see, h times the integral of x minus x to the fourth over 4a to the third, evaluated from 0 to a. And that will be h times a minus a to the fourth over 4a to the third. And that goes away there. And this all becomes, okay, so this will be 3/4 a, and so then that will just be 3a h over 4 for the area. So we have that. That's one useful thing. Now, we'll need our QY, our first moment of area off of the y-axis, which is the integral of x dA. Now, our x dA will have our, for our purposes here, for QY, our differential element will be like this. It'll be dx, and then it will be, let's see, it will be what? It will be, yeah, h minus h over a to the third, x to the third for our height. So then we'll have, I'm just going to go ahead and pull out the h again, the integral again from 0 to a of h minus, no, I'm not going to have the h in there, sorry. I'm going to have x in there. X times 1 minus x to the third over a dx, which equals h times the integral from 0 to a of x minus x to the fourth over a dx, right? Yes. Which equals h times the integral of x squared over 2 minus x to the fifth over 5a evaluated from 0 to a. Any questions on that so far? Yes?
In the denominator, is it a to the third instead of a?
Is it a to the... Yes, it is. What's the power of a among friends? There you go. That a to the third was always there. I have no idea what you're talking about. Okay. And so then this will be simply h times a squared over 2 minus a to the fifth over 5a to the third becomes squared. So this is h times a squared over 2 minus a squared over 5, common denominator, h times 5a squared over 10 minus 2a squared over 10, and this comes to, let's see, that's h a squared 3 over 10, like so, and that's qy. And finally, so we have our a, we have that, we have our qy, and our x bar then is going to be equal to qy over a equals 3h a squared over 10. Here I'm just going to be lazy and just go ahead and just straight up multiply by the reciprocal. I'm dividing by a, it's a fraction, I'm just going to just multiply by the reciprocal. 4 over ah over 3ah. 4 over 3ah. The 3 cancels out, the h cancels out, the h cancels out, the a and the a cancel out, and I get 2/5 a for x bar. Questions on that? Huh? That's the x bar. We still need to find the y bar. Okay, questions on this? All right. I'm going to need another slide.
Excuse me.
So I'm going to do some transposition again. I'm going to do some transposition here. So I'm going to need, let's see, I'm going to need the equation. I know that, okay, no, this is best done just as a, in the thing. Okay, so I'm going to need the equation, which is y equals h minus h to the third over a to the third, h over a to the third, x to the third. So again, all I'm doing on this next slide at the start is just copying down what I had previously. And I also know that a is 3ah over 4. And just because I'll want to write it down later, I also know that x bar, the x coordinate of the centroid, is 2/5 a. So those are the significant details from the last slide that we'll need. So then, let's say y minus h equals negative h over a to the third, x to the third. Then, so I'm just solving this for x basically. H minus y equals hx to the third, a to the third over a to the third. 1 minus y equals x to the third, y over h equals x to the third over a to the third. And then finally, not finally, I guess, x to the third equals a to the third times, actually I'll just leave it out for now, 1 minus y over h, like this. And then finally, let's see, that looks good. X equals the cubed root of all this nonsense. A to the third. I didn't realize you worship Newton. No? Okay. I just heard someone said at the integral, like, oh my god. I'm like, you worship calculus? Okay. I'll respect your religious beliefs. Equals a cubed root of 1 minus y over h. And at first glance, it may seem like this is going to be a horrible integral, but it's actually not going to be so bad. We get to do u to u integration here. Yay! Okay, I think, let me, unless there's an easier way to do that. Huh?
You just do sub? Or do you just do u equals 1 minus y?
Well, the issue, actually, this is maybe a little more complicated than it seems at first glance. Let's see, how can we do this? Because here's the issue, I'm looking ahead, and I'm going to have my dA is going to be horizontal, right? My dA is going to be horizontal, like this.
Why you should pick horizontal rather than vertical?
Because we're doing we need to have the, because there's going to be a y component in there, right? The qx, remember? Qx is the integral of y dA. And this y is what's going to give us trouble in the integral. That's the issue I'm seeing. Okay. Uh-huh. It won't just drop off, no. The integral of, so again, if we look at this, if we look at our dA, like this, we're going to have a dy and a cubed root of 1 minus y over h for our area, for our x value, for our width. And then the qx, the first moment of area off of the x-axis, is going to be the integral from 0 to h of a times x. That's from the formula. Well, let me just show the more clearly. Let me show the formula. Again, qx is the integral of y dA. So that's the integral of y times a cubed root of 1 minus y over h dy, which is then equal to, let's see, I can pull out the a, y cubed root of 1 minus y over h, like that, dy. All right. Oh, and it's from 0 to h.
This is QX.
Yes, this is qx. All right, now here's the trouble. I could do a u du, but that's not going to work, is it? I could do a u du, but that's not going to work, is it? Because we're still going to be stuck with the y, aren't we? Let's see. Any thoughts? Yeah, it's something like it's integration by parts or something like that. I don't know if I want to mess with it. I would probably consult a calculus table and look up I'd probably consult an integral table, look up the form of integral that we need to use. But all you got to do is get this integral here, and then simply say that that y bar then is qx over a, like that. Again, once you set up the integral, sometimes you'll just need to consult a table of integrals to solve some of these, or dig up some info on integration by parts, etc. Okay, other ideas, other thoughts on this, I mean, just to say. I think that's about as far as I'll take it for here, but that's the general idea. Once you have it set up, sometimes you do need to go and look up in an integration table how to handle that, but that's the general idea. Yes?
So I know this is kind of like, but on the exam, so if we get this kind of integral, we'd be expected to know how to solve it by now.
Okay. So there's that. Let's see, we're still good here. Okay, so let's look at this one here. All right, this is another one here. So we have an ellipse. We have an ellipse. Oh, we want actually this region here. So this one's a little bit tricky. And let's see. What could we do? So let's think about this. We could try, yes?
In practice, is there a formula in the table for an ellipse or a quarter ellipse?
You'd have to check the table.
So like in practice though, if we weren't asked to do it by integration, we just do the square minus the quarter ellipse.
Possible. Possible. Okay. Let's see. So how are we going to do this? We can say, let me first solve this in terms of x. X squared over a squared equals y squared, or maybe 1 minus y squared over b squared. And x squared equals 1 minus y squared over b squared. Well, actually, a times y squared a over b squared. Yuck, what a mess. What if we did this in terms of polar coordinates? What do you think?
No way.
No way? Could try that. That might be easier because I'm seeing that this integral is not going to be particularly easy to do. It's not going to fall into place very easily with like well, actually, maybe.
The solution uses a sine cosine solution.
Yeah, I was taking a look at that, and there were some parts that I was having trouble figuring out what they were doing exactly.
Oh, you too?
Okay, so here, let's see, what else might we do?
It's supposed to be a squared minus y squared times a squared b squared.
Oh, a squared, yeah. It doesn't really matter anyway. I probably should solve this for y anyway if I'm going to find the area of it. Okay. So let's say I do y squared over b squared equals 1 minus x squared over a squared. And y squared equals b squared minus b squared x squared over a squared. All right, what else could we do? Let's see. If I try to find the area of this, again, it's see. Here's the problem. Do you see the problem with trying to find the area of this? The area, again, the issue with this, let me show you, is that it's not going to be a nice thing we can solve with UDU substitution or something like that. We'll have to use an integral table again. I'm trying to avoid that. Equals, that looks like b, no. Let me just get it like this so you can see what I'm talking about. The square root of b squared minus b squared x squared over a squared, right? And if I try to integrate this, I'm not going to have a good time because there's not an x within here. Yes.
You can't factor out the b squared from it.
That the b is just a constant. It doesn't matter. I mean, see, the b doesn't really matter. It's just b times 1 minus x squared over a squared. The problem is the x squared. If there was an x out here, it'd be very easy to integrate. But let's see. What if we did it in terms of polar coordinates? Something like that. What if we say that x equals r cosine theta, right? And y equals r sine theta. Maybe something like that. Could we do that? So then we'd have, instead, well, we would have, for this line here, instead of having y equals b, we would have r sine theta equals b, right? So that would represent this line, r sine theta equals b for that one. And then x squared over a squared plus b squared over a squared would equals 1 could be reduced to, let's see, r squared cosine squared theta over a squared. Oh, wait a minute, what happened here? X squared, r squared cosine theta over a squared plus r squared sine squared theta over b squared equals 1, right? And let's see. I don't know if this is going to get us anywhere, but it's something like that. Anyway, I'll put the solution to this one on the page. This one's just kind of annoying. So let's see. I can show you what the solutions manual does. Let's do that. See, let me show you what they do. They have this element of integration, which they say for the they're trying to get the integral of a, I believe, and they just run through it, etc., using various applications of polar integration, and they get it like that. Okay, I don't know if we necessarily have time to work all the way through that, but that's the general idea. It's very similar to the other ones. You'll just need to sit down with your calculus book and review some things on polar integration. Okay. All right, and this is really the same idea. I've already told you the answer to that.
No, I didn't hear it. I'm sorry.
Okay. So here, the first thing I can say on this one is that x bar is obviously 0. It's obviously symmetric about the y-axis, so x bar is going to be 0. So we only need to concern ourselves with one piece of this. We only need to concern ourselves with one piece of this and nothing more. Okay. So, let's see. What might we do? Well, this equation here is going to be the square root of, well, let's see. I know the equation for a circle in general is, the equation for this one is going to be x squared plus y squared equals r2 squared for the outer one. And for the inner one, it's going to be x squared plus y squared equals r1 squared, like this. And then, let's see, we need to get, well, area is easy enough. We don't even need to do an integral for that. That's just pi. Again, I'm going to worry about only the part in the first quadrant. The part in the second quadrant doesn't exist anymore. Pi r2 squared over 4 minus pi r1 squared over 4. And this is then pi over 4 times r2 squared minus r1 squared, like so. Then let's see here. Actually, this one might not be too bad. Let's see. If I can say the q, so that's going to be our a that we'll use. The q, we're going to need qx to find the y bar equals the integral of y dA equals, and then one of our components. Okay. Let me solve these equations. So the outer equation is going to be x equals the square root of r2 squared minus y squared. And the inner equation is going to be x equals the square root of r1 squared minus y squared, like so. And then, let's see, qx. So our differential element is just going to be the difference between these. So our differential element is going to be a, actually it's going to be more horizontal than vertical. It's going to be a horizontal differential element. So it's going to be dy, and it's going to be these two square roots minus each other. So the outer minus the inner. So r2 squared minus y squared minus the square root of r1 squared minus y squared. This one I can just use u to u, so I'm not going to need to consult an integral table. So then this is just y times the square root of r2 squared minus, oh, I need the integral from, let's go from 0 to r2. No. r1 to r2. No, actually, well, it should be 0 to r2 or r1 to r2. Let me think about that. Yes.
Why was it pi squared over 4 before that and then not over 2?
Oh, what are you talking about?
For the first part when we found A.
The area, not A.
Yeah, A equals pi r squared over, or r2 squared over 4. Why'd you decide that 4 then?
Quarter circle.
Okay.
Okay, so let's think about this. I'm trying to think if there's a better way between just, we could do it in pieces and then just subtract. Maybe it's better to do it that way. Let me think about that. I'm trying to get a, let's see. No, that should work. Yeah, that should be fine. Yeah, no, that'll be fine. Okay. Integrated from perhaps 0 to, let me think about this, because if I do, I'm trying to think if that's some bounds that will make sense without screwing things up. Because if I do 0 to R1, well, then we're not including this part. If I do R1 to R2, then I'm not getting this part down here. And if I do R1 to R2, then I'm missing this part down here. I think we're going to have to break this up into 2 pieces. Yes?
So is there any way you can express your centroid coordinates as r theta?
Yes, you can.
For the next few lines? Yeah.
Okay, so what I'm going to do is I am going to break this into 2 pieces. I'm going to find the centroid of the inner piece and the outer piece and then combine them. So, inner piece centroid. And so now let me just go back and say, you know what, forget this. Let's just do everything for the inner piece first. Could really use some inner piece right now. So the inner piece, I'm just going to break this up. And it's just this piece here, R1. The area is just simply going to be negative pi R1 squared over 4. Okay? Then, yeah, that works fine. Then I'm going to use again a dy, but this will simply be that's just going to be x equals the square root of y squared, or sorry, r1 squared minus y squared. R1 squared minus y squared, like so. Then I'm going to say, all right, qy, or qx, sorry, is equal to the integral from 0 to r1 of, let's say, y dA. So this is going to be y times root r1 squared minus y squared dy. And then I want to make this 1/2 integral 0 to r1 of 2y root r1 minus y squared dy. I'm going to let y, or so let u equal r1 squared minus y squared. So du is then just going to be 2y dy. Okay. Let's see. So this will then be the integral of 1/2 times the integral from r1 squared, 0 for y, it becomes r1 squared, to r1, which is going to be 0, of just, that is the square root of u du. Any questions on what I'm doing so far? Yep, hopefully you've seen this before. U du integration. All right. Then this will go here, and I will get 1/2 let's see. So this is just u to the 1/2. So we'll have u to the 3/2 and then 2/3, right? Any objections to that? Okay. And then r1 squared to 0. And then, let's see. Although, are we going to end up with a negative area if we do this? Negative q. Actually, that's fine, I think. Well, huh? Where am I at? Yeah, let's think about that. Is that we'll double check the X bar with the table. There should be a formula for this one in the table. Let's see then. So then this is then 1/2 square root of, well, the thing is, the problem I'm seeing with that is that the area, what if it wasn't a negative area? What if it was a positive area? What if it was a positive area? I'm very wary of saying, oh, the negatives are just going to cancel out. That's still bothering me a great deal. So you know what I'm going to do? I'm not going to do the bounds integration. Maybe that's screwing us up somehow. I'm just going to take the integration and plug back in the u after I'm done. Maybe. Let's see if that works. Then I just have, again, 1/2 the integral from 0 to r1 of, then this is just u, no, square root of u du. And this will go up here again. And I will get 1/2 times u to the 3/2 times 2/3. All right. And then let me evaluate it by plugging back in the y. So this is then, let's see, that is 1/3. This combined with this, 1/3 r1 squared minus y squared, and this evaluated from 0 to r1, and this to the 3/2 power. Any objections to this so far? And then, let's see. When I plug in r1 squared, this is going to be 0. Oh, wait a minute. Huh. Never mind. Maybe it's negative no matter what we do. Interesting. Okay. Maybe just the way we set it up, it's going to, why would that be negative? Let me think about that.
Is the du supposed to be a negative 2r?
Is the du supposed to be a, oh, that's why. Derp. That's the error. No wonder why I was coming out negative. Derp, 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 derp. Oh, it's Friday. It's like a Friday.
Last day of the work week is maybe what happened.
Huh?
Last day of the work week, we couldn't understand that.
Negative 2y dy. There we go. That'll do it. Okay. I swear I'm sober. Anyway. Okay. And then, let's see. So this is then going to just be the integral of, so if I put in 0 for y, I will get r1 squared, right? Go away, go away, go away. I'm just going to go to the next line right now. So we will then have the integral of, we're going to have 1/2 the integral from, let's say, r1 squared to 0 of, let's say, that's just square root of u du now, isn't it?
Maybe negative 1/2?
Would it be negative? Yes, it would be negative 1/2. Yes, thank you. Because we have the negative du there.
How did it switch how did your integral flip from going 0 to R1 and...
Oh, where the bounds came from is I put in 0, the old y, into the u expression. And I put in R1 into the old u expression. So then this is negative 1/2 times, looks like, now we have 2/3 u to the 3/2 from 0 to R1 squared. And the 0 just goes away. So then this is negative 1/3 R1 squared to the 3/2, which will just be, well, actually negative here. So let me break this up. I think it's a little bit confusing when I'm writing this. Negative 1/2 times 0 minus 2/3 R1 squared 3/2, like so. So then I'll have negative 1/2 times negative 2/3, and this is just going to be R1 to the 3rd. R1 to the 3rd, and this is then R1 to the 3rd over 3. Yay. Okay. R1 to the 3rd over 3. And then x bar, or actually y bar, and again this is qx. Y bar equals R1 to the 3rd over, oh, let me write it out so you don't see it. Let me write out where this is coming from. Y bar again equals qx over a, which will be equal to R1 to the 3rd over 3. I'm going to just multiply by the reciprocal. 4 over pi R1 squared. Boom, boom. And this comes to 4 R1 to the 3, or to, not to the 3, sorry, over 3. Over 3 pi. Huh? The inner piece is negative. I'm going to ignore that. That we're only going to use that negative when we compute the combined centroid. Okay. Now, since this is just a quarter circle, right? Since we have just proved that the y bar centroid of a quarter circle is 4 R1 3 pi, right? So that's the same for the second one. So second piece, the second piece must have, so let me just say, so this is in general A1 equals pi R1 squared over 4. Well, the second piece, by the same argument, I don't need to do the whole integral again for the exact same shape. It's obviously just going to be substituting R2 for R1. It's the same exact shape. It's centered at the same location. It's oriented the same way. Yes?
So when you're talking the second piece, you mean like the whole thing?
I'm talking about the whole circle, yes. The whole quarter circle without the whole. Okay. Just R2 here. So R2, so let's see, A2 then obviously is just pi R2 squared over 4, and y bar, let me call this y bar 1, and y bar 2 is then pi R2 over 3 pi. Like so. And then, let's see, then we just combine it all together. Oh, yeah, sorry. 4 pi. They look so similar. So this is then going to be, all right, so let's think about this. This is going to be, where is this? 4 R1 over 3 pi. Actually, I'm going to have to really squeeze this in here, so. Y bar equals, I'm going to try to write small, 4 R1 over 3 pi. This is Y bar 1 times the area 1, which is pi R1 squared over 4 plus 4 R2 over 3 pi times 2 pi R2 squared over 4. And all of this divided by the sum of the areas, which is going to be pi over 4 times R1 squared plus R2 squared. And then the 3 and the 4 and the pi's cancel out. Yes.
Would it be minus R1 squared because of the negative area?
Oh, yes, thank you. I need to do that. Thank you. Like that. And this one needs to be negative as well, doesn't it? Yes. Yes, it does. Sorry about that. And the pi's and the 4's go away. So this is going to be, let's see. This looks to me like R2 to the third over 3 minus R1 to the third over 3 divided by R2 squared minus R1 squared times pi over 4, like so. And then I could probably simplify this as, I'm guessing there's some difference of squares thing we could do with this, but I'm feeling lazy. I just want to get this done.
Can you factor out the 1/3 from the
Yes, like this we can do this. Obviously, that's the trivial thing, but I'm talking about the r's here. R2 to the third minus R1 to the third over R2 squared minus R1 squared, like so. And I'm just going to leave it at that. We could probably do, I think we can pull an R2 minus R1 out of this one, but whatever, I'm feeling lazy, so that's okay. I don't feel like doing long division today. Questions on that?
Only question.
Yeah.
Can we just do this with a tabular method and just see that?
I mean, they asked us to do it via, the question was, can we do this via tabular method? The problem asked us for yes, you can look up the formula for the centroid of a quarter circle in a table, but it specifically asked us to do it via integration, so I would feel wrong not doing some sort of integration in it. And I probably cheated I probably cheated breaking it up into 2 pieces and using formulas to combine them. If we were to do it real properly, we probably should have put it into polar form first and then done a polar integral, but I don't want to dig through my calc book and look up the subtleties of polar integration right now. Yes?
That was the question, like why didn't we use polar?
Because I'm feeling lazy. That's why. Okay. Anyway, but you could do it that way. Either way. On the exam, you're not going to have anything terrible. You're not going to have anything terribly complicated. So I just wanted to illustrate how difficult some of this stuff can get. But all right. So questions on centroids.
These 3 problems, there's clearly a sequence of steps you're going through. Can you go over those steps?
Sequence of steps.
Yes.
Set it up. Take the integral. Divide.
To abbreviate it. The book throws out solutions, step 1, step 2,
Mm-hmm.
and you're going through and you're taking, let's see, you're taking the area.
My general sequence of steps for these is I first go and I take a look at the problem and realize, look ahead, see how it's going to sort of work out. I set up my first thing I do is find my area via integrating usually with respect to x or respect to y. Okay, I find my area. Then I find my qx by integrating. I set up the integral. I find the appropriate horizontal um, differential element. You got to set that up depending on what exactly you're looking for. You run through the integral, and that's pretty much it. So, setting up the differential element is probably the most important part.
So if we mess that up, then we mess it.
Exactly. Okay. So, what do y'all think of centroids?
Messy.
Messy. That's messy. I think they're messy. All right. It is now time to move on to the final chapter of the course. Yay, finally, right? Okay. Oh, also, there is one other, actually, before we move on, there is one other thing I would like to mention. Centroids, I don't think we discussed this, but I probably should mention it. Centroids and distributed loads. We've used this a little bit, and in previous parts of the class, you were really confused by this. But that's okay. For the purpose of calculating external reactions, on a body, the forces, or a distributed load on a body can be replaced with equivalent loads, or I should say with an equivalent load, singular, acting through the loads centroid. Let me underline this in a different color to make very clear what I'm talking about and the subtleties here involved. So the loads centroid, and for the purpose of calculating external reactions. That's the only thing this is good for. Cannot be used to calculate internal forces. You can use this method to calculate the external reactions on a beam, or say on a body, or say on a beam, but you cannot use this to say find the bending moment at a point. You still need to do the method of cuts or inspection, etc., etc. Okay, what do I mean by this? If you have a beam, say I had a beam, and maybe this is simply supported. And, oh, let's say for some insane reason there's a semicircular load on this structure. So let's say this starts at, and let me just say semicircular load. I don't know why you would have a semicircular load on structure, but you could. How would I get a semicircular load on a beam? Yeah, that's the only way I can really think of is literally put something semicircular shaped, a big block of metal cut out like a quarter circle. That'll get you a semicircular load.
Put half an eagle off like that.
Yep. Okay. So there's that. Now, we remember. Now we can. Oh, I chose this because we figured out in the previous slide that the centroid of a quarter circle is 4r over 3 pi, right? Here, and let's say this is 12 feet, and maybe the peak here is, oh, I don't know, um, 1.5 kips per foot. Okay. So let's see. If I go and what I mean by an equivalent load is I can find the total load of this and simply multiply. Or not simply multiply. I can find the total load, and the reactions will be the same as if I replace this with an equivalent load about the centroid. So this would be AY and BY. Let's say I wanted to find AY and BY. What could I do? Yeah, well, let me find the equivalent point load first. Huh?
It's just going to be, well, no, you have to multiply by 12.
Yeah. Wait a minute, how's this gonna work? Does a semicircular load even make sense? Hmm. Yeah, I don't know if we can do this. Maybe I'm getting a bit ahead of myself. Maybe a semicircular load isn't the best idea.
Maybe we should do that. I don't know.
Maybe we should do a parabolic load instead. I'm trying to think of how I'm gonna find the area of this, and that's gonna be a little complicated, isn't it? Okay, so let me cop out and say that this is a parabolic load instead. So this is a parabolic load.
Wouldn't that just be the quarter elliptical area?
Oh, the quarter elliptical area. Why didn't we do that? Yeah, I guess that would work. Yeah.
No, it's an ellipse.
Yeah, it has to be an ellipse because they're not the same unit. So elliptical load. That'll make a little more sense. I can live with that. So let me go to the table and find the formula for the area of a quarter ellipse. Pi AB over 2. Right. Let me see that. Area pi AB over 4. Yes, pi AB over 4. Yes. So here, the formula for the area of an ellipse is pi AB over 4. But in this case, our A is going to be 12 feet. Our B is going to be 1.5 kips per foot. What's that variable? P? That's the equivalent point load here. The magnitude of it, anyway. Over 4, you could call it anything you like. I just thought P might work for the point load. And let's see. 12 times 1.5 over 4 is 4.5 pi kips. And then the centroid of this is going to be at, let's see, for the x bar, which is what we're interested in, is 4a over 3 pi. It's 4a over 3 pi. So x bar equals 4a over 3 pi, which equals 4 times 12 over 3 pi, which is then 16 over pi, right? Yeah, 16 over pi. 16 over pi feet. Lovely. So then I have a beam like so. Actually, maybe I'll draw it on the next page. So what I've done is I've replaced this distributed load with the following system. I have a beam. Instead of that ugly distributed load, I now have a nice pretty load in terms of pi. This is 4.5 pi kips. And we have AY and BY. And this thing is at a distance from the left of 16 over pi feet. Is that realistic? 16 over pi, what is that approximately? That's about 5 point, yeah, that's about right. That looks about right. 16 over pi. 16 over pi feet. So now it's just a simple balance of moments, etc. Sum of moments about A, I'm going to have negative 4.5 pi times 16 over pi plus BY times the 12 feet equals 0. Pi goes away. And BY is going to be 4.5 times 16 over 12. BY is 6 feet, or sorry, 6 kips. BY is 6 kips. And then, let's see. Does that make sense? I'm thinking. Yeah, that'll work. Then, sum of forces in the y direction will give me negative 4.5 pi plus 6 plus by equals 0. So by is equal to 6. Oh no, 4.5 pi minus 6.
It's AY, right?
Oh, sorry. AY, by, it's all the same. Oops, sorry. AY, by, they're all in terms of y. AY equals, that should be an AY here. AY, sorry, is then 4.5 pi minus 6 kips. And for some reason I have this expressed in exact mode instead of decimal mode. I'll make sure that's greater than 6. Should be. Yeah, it is. Okay, so questions on that. Again, this is for the purpose, when can you use this?
We have a beam subject.
Yes, but what application of beam theory? What can you do? Like, can you use it to find internal moments in shear? No, you cannot use this to find internal moments in shear. In order to do that, you still need to take cuts, and you still need to do it by inspection. So again, if I wanted to find the moment somewhere in the middle, I would still draw a parabolic load, do integration, etc., etc. All right, and that's it for centroids. Okay, let's take a short break, I guess, come back, and we'll look at moments of inertia. Seems like a reasonable cutting off point.